Last month, on June 22nd, 2026, a paper was published in the journal Nature that quietly changed how we understand where things come from in this galaxy. A team led by Martin Cordner at NASA's Goddard Space Flight Center had used the James Webb Space Telescope to read the isotopic chemistry of a comet that is not from our solar system, not from our star, not from anything within trillions of miles of Earth. And what the isotopes told them was that this object, this frozen chunk of ice and dust, roughly 2.6 kilometers across, likely formed between 10 and 12 billion years ago. Our sun is 4.6 billion years old. This comet may have been drifting through the galaxy for more than twice the entire lifespan of our solar system. Cordner told reporters it is probably the oldest object ever observed passing through our solar system, but the age is not even the strangest part. The strangest part is what its chemistry looked like when Webb pulled it apart wavelength by wavelength, because the chemical fingerprint of this object does not match anything in our solar system. Its water contains roughly 30 times more deuterium than any comet native to our sun. Its carbon isotope ratios are unlike those seen in any solar system body, any nearby interstellar cloud, or any planet-forming disk around any young star we have ever studied. And for months, it was venting nickel gas into space without the iron that should always accompany it, a chemical signature so unusual that it drew a peer-reviewed SETI search with the Allen Telescope Array and a public debate between Harvard's Avi Loeb and every other research team studying the object. The SETI search found nothing artificial. The nickel mystery was eventually explained by temperature-dependent chemistry that had never been observed on a comet before, but the object itself remains unlike anything science has ever had the tools to study. Stay with me because this is the story of 3I/Atlas, the first interstellar visitor humanity was actually ready for, and what it is teaching us about the universe is something we could not have learned any other way. Subscribe now if you want more stories like this, because what is coming out of interstellar comet science right now is rewriting the textbooks on planet formation, and I am covering every piece of it. The story starts on July 1st, 2025, at a modest observatory in Rio Hurtado, Chile. The facility is called ATLAS, short for Asteroid Terrestrial Impact Last Alert System, and its job is to scan the sky night after night looking for anything that might be heading toward Earth. On that night, it flagged a faint point of light moving in a way that did not match anything in its catalog. Within days, astronomers around the world had confirmed what the orbit was telling them. This object was not looping around the sun the way every comet and asteroid in our solar system does. It was moving on a hyperbolic path, a wide open arc, the kind of trajectory that only makes sense if something came from outside the sun's gravity entirely and is just passing through. Its orbital eccentricity came out to approximately 6.14. To put that number in context, anything above 1 means the object is not gravitationally bound to the sun. Oumuamua, the first interstellar object detected in 2017, had an eccentricity of roughly 1.2. Borisov, the second, found in 2019, had about 3.4. This one was at 6.14, the most extreme trajectory ever recorded for any object passing through our solar system. It was moving at roughly 137,000 miles per hour when it was discovered, still well outside the orbit of Jupiter, and it was on a retrograde path, coming in nearly opposite to the direction most objects in our solar system travel. There was no ambiguity. This object had originated somewhere else entirely. It was designated 3I/Atlas. The 3 means third, the I means interstellar. And here is why this discovery was different from the first two in a way that changes everything about what we can learn. When Oumuamua was spotted in October 2017, it was already on its way out. Astronomers had only weeks to study it before it faded. It showed no visible coma, no tail, no outgassing that instruments could detect, and its unexplained non-gravitational acceleration sparked a debate that remains unresolved to this day because the data was simply too limited to settle anything. When Borisov arrived in 2019, the situation was better. It was clearly a comet with a visible coma and tail. But Webb had not yet launched, and the instruments available could only resolve its composition in broad strokes. When 3I/Atlas was discovered on July 1st, 2025, for the first time in history, astronomers caught an interstellar object on its way in, well before its closest approach to the sun, with the most powerful suite of telescopes ever assembled already operational and ready. Webb was calibrated. Hubble was available. The Vera C. Rubin Observatory, which had just begun operations, had actually already captured the object in survey images as early as June 24th, a week before anyone knew what it was. NASA's TESS satellite found pre-discovery data showing the comet was already active by May 7th, at a distance of 6.4 astronomical units from the Sun. ESA turned multiple interplanetary spacecraft toward it, Mars Express, ExoMars Trace Gas Orbiter, JUICE, and the SOHO Solar Observatory caught it as it passed through perihelion in late October. For the first time, an interstellar visitor was studied by an Armada. The first major surprise came in August 2025 when Webb and NASA's SPHEREX mission got their initial look at the gases pouring off the comet as it heated up. In a solar system comet, you would expect water vapor to dominate that outgassing because water ice is the most common frozen material our comets carry. That is not what these instruments found. The coma of 3I/Atlas was overwhelmingly carbon dioxide, roughly 95% CO2, with water accounting for only a small fraction. Webb also detected carbon monoxide, carbonyl sulfide, and water ice particles mixed into the coma. A CO₂-dominated composition at that distance from the Sun is unusual. It suggests the object formed somewhere extremely cold, far colder than the region where our own comets condensed, in a part of a stellar disk where carbon dioxide ice could form and survive more easily than water ice. Cordner, who led the Webb observation team, said afterward that when he loaded up the first spectrum, he was blown away. SPHEREX followed up in September 2025 and confirmed organic molecules present within the coma as well, adding another layer to a chemical picture that was already looking unlike anything in our solar system. If you are the kind of person who stays for the real science instead of clicking away, drop a like right now because it genuinely helps this kind of content reach more people who want to hear it. Then came the anomaly that drew headlines for months and pulled this story out of specialist journals and into mainstream coverage. In October 2025, a research team using the UVES spectrograph on the European Very Large Telescope in Chile detected nickel gas in the comet's coma. That alone was not shocking. Nickel vapor has been seen before in a handful of solar system comets. What made this different was what was missing. Every time nickel vapor has been detected venting from a comet before, it appears alongside iron, because the two metals are forged together inside dying stars and supernovae and travel through space bound to each other as what researchers sometimes call cosmic twins. In 3I/Atlas, the nickel signal was strong and the iron signal was nearly absent. The detection was corroborated by additional data from the Keck 2 telescope in Hawaii. On its own, this created a genuine scientific puzzle. Comets are generally too cold for solid metal grains to sublimate directly into gas. Something had to be releasing the nickel through a different chemical pathway. The leading natural explanation involved a class of compounds called nickel carbonyls, specifically nickel tetracarbonyl, a volatile organometallic molecule that can break apart under sunlight at much lower temperatures than would be required to vaporize iron from its own more stable compounds. Avi Loeb, the Harvard theoretical physicist, pointed out publicly and repeatedly that nickel without iron is otherwise mainly associated with industrial refining processes on Earth. He rated 3I/Atlas a 4 on his own anomaly scale and suggested a possible technological origin. It is important to say clearly that this was and remains a minority position within the scientific community. The overwhelming majority of astronomers working on the object, including the teams who made the detections, favored natural chemical explanations rooted in the comet's unusual formation environment. And the scientific community did what serious science does when a legitimate question gets raised. A team of researchers pointed the Allen Telescope Array, a radio observatory built specifically for SETI searches, directly at 3I/Atlas during its passage, systematically searching across a wide range of frequencies for anything that might indicate an artificial transmitter. The result was a clean non-detection. No artificial signal was found at any frequency the array could monitor. That detail rarely makes the dramatic headlines, but it matters because it shows the process working exactly as it should. A question was asked. An instrument was pointed, an answer came back. Now here's the part that most coverage of the nickel story missed, and that only became clear in 2026. A study led by Hutzemakers and colleagues, published in Astronomy and Astrophysics, tracked the nickel-to-iron ratio in the coma as 3I/Atlas moved closer to the Sun and warmed up. The title of their paper tells the story, From Extreme to Normal. As the comet heated, the iron signal appeared. The ratio normalized. The temperature-dependent carbonyl chemistry explanation held up exactly as predicted. Nickel tetracarbonyl has a lower sublimation point than iron pentacarbonyl. The nickel appeared first because it vaporizes at lower temperatures. The iron appeared later because it requires more heat. The staggered release was not evidence of something artificial. It was evidence of temperature acting as a clock inside an ancient frozen body, releasing metals in sequence as heat slowly diffused through billions of years of accumulated ice. The anomaly was real. The explanation turned out to be natural but previously unobserved on any comet. A new class of cometary chemistry documented for the first time on an object from another star system, now the age. This is the finding that lands hardest once you sit with it. The Nature paper published on June 22, 2026, detailed Webb's measurements of two specific isotope ratios in the gases 3I/Atlas was releasing. The first was the ratio of carbon-12 to carbon-13. Almost all carbon in the galaxy gets produced inside massive stars. As generations of stars live, die, and enrich the interstellar medium with new material, the proportion of carbon-13 relative to carbon-12 gradually increases over cosmic time. Material that formed earlier therefore contains proportionally less carbon-13. What Cordner's team found was a carbon isotope ratio containing far less carbon-13 than anything measured in our solar system, in nearby interstellar clouds, or in planet-forming disks around other young stars. Working backward through galactic chemical evolution models, they concluded the object likely accreted its ice roughly 10 to 12 billion years ago, during a period of intense star formation astronomers call cosmic noon. The universe itself is 13.8 billion years old. This comet may have formed when the universe was less than a quarter of its current age. A complementary study by Cyrielle Apetom of the University of Edinburgh, using the VLT's UVES spectrograph, independently confirmed the carbon isotope findings and added nitrogen isotope measurements that further supported the ancient metal-poor origin. Both papers point to the same picture. 3I/Atlas formed in the outer disk of an older, lower metallicity star system, in conditions colder and more heavily irradiated by ultraviolet light and cosmic rays than anything in our own solar neighborhood. The second isotope ratio was deuterium-to-hydrogen in the comet's water. Deuterium is a heavier form of hydrogen, and the D/H ratio in a comet's ice carries information about the temperature and radiation conditions under which that ice formed. 3I/Atlas showed roughly 30 times more deuterium than solar system comets. That level of enrichment forms in environments colder than about minus 243 degrees Celsius, and it is consistent with billions of years of galactic cosmic ray bombardment altering the isotopic structure of the ice as the object drifted between star systems. Cordner said it in his own words. Our James Webb Space Telescope observations tell us that the planet-forming environment of 3I/Atlas's host system was distinct from our own solar system. It was likely colder and less metal-rich, while being more heavily irradiated by ultraviolet light and cosmic rays, and then he added the line that shifts the whole frame. On the one hand, we get direct insight into that distant time and place. On the other, we learn something about how unusual our own solar system may be. Here is what I want you to take away from all of this. Every comet in our solar system formed from the same disk of gas and dust that built the planets. Studying them tells us about our own origins. But 3I/Atlas is a physical sample of material that condensed around a completely different star, under different temperatures, at a different point in the galaxy's history, and drifted here across billions of years without ever being disturbed by our sun's heat until October 2025. That gives researchers something they have never had before. A direct chemical comparison point to test whether the process of building icy bodies works the same way everywhere in the galaxy, or whether it varies depending on where and when a star system forms. And the early answer, based on everything Webb and Hubble and the VLT and ALMA and every other instrument that studied this object have found, is that it varies significantly. The specific mix of ices, the isotope ratios, the metal chemistry, all of it points to a formation environment distinctly different from our own. 3I/Atlas is not a discovery that rewrites physics. It is a discovery that gives astronomers their first real outside data point. And outside data points are how you find out which of your assumptions were actually just local habits all along. Stephanie Malam of NASA Goddard and co-author of the Nature study put it in terms that reach beyond the chemistry. For us as scientists, finding these rare isotopes is fascinating, but the bigger picture here is looking at the possibilities of prebiotic chemistry elsewhere in the galaxy. Right now, 3I/Atlas is somewhere past Jupiter's orbit, moving away from us at more than 60 kilometers per second, carrying chemistry that was locked into ice before our sun had even finished forming. It will never slow down, never turn around, and never pass this way again. Every instrument that is ever going to study it up close has already had its turn. What is left behind is a full data set sitting in the archives of Webb and Hubble and the VLT and a dozen other observatories. Records of a piece of another part of the galaxy that happened to drift close enough for us to actually measure once before it disappeared for good, and it will not be the last. The Vera C. Rubin Observatory, now operational in Chile, is specifically designed to catch fast-moving faint objects early. Current projections estimate it may identify dozens to hundreds of interstellar objects over the coming decade. Somewhere out there tonight, a fourth interstellar object is already inbound, and right now nobody on Earth knows it yet. If this kind of deep, research-grounded space science is what you come here for, subscribe right now and turn on notifications. The next interstellar visitor could be detected at any time, and when it is, you are going to want to have already understood what you are watching. Drop a comment with what surprised you most and share this with someone who needs to hear it, because this story deserves a far bigger audience than it is getting. Thanks for watching, and I will see you in the next one.